evaluate finite limits or one-sided limits, if they exist, using graphs. Here before you have the graph of a function. The function is written up in the corner. It's x squared minus 2x minus 15 over x minus 5. What we want to do is take a look at the limit of this function as we approach 5 from the left and the right. And what that means is that as we approach 5 from the left and get closer to 5, and right and get closer to 5, what we're asking is, are those outputs getting closer to a particular output? So let's look at the definition and see if we can make heads or tails out of it. The limit of a function as x approaches a is equal to L, and we denote it, x is approaching a. In this case, a is what? A is 5, is equal to L, is equal to that output that we're looking at, and that is provided that the following happens, that the values of the outputs can get as close to L as we like. All we have to do is take values of x to be sufficiently near or close to a, and we don't really care what happens at x equals a. So if you and I trace the graph just for a sec, and I go ahead and take a look at getting close to 5 from the left and then getting close to 5 from the right, notice what happens. I'm going to go ahead and mark here. These outputs are getting very close to 8 when I approach from both sides. So how would we write this? Well, the way we would write it is we would say the limit as x approaches 5, because that's the input, of my function is equal to 8. And again, notice that the function itself is not defined at x equals 5, and that's okay. What we're worried about is what happens when we near 5, not at 5. Now, one last point, just very briefly, is that if you and I take a look at the function, f of x, I could rewrite it as, and I'll just factor the numerator, as x minus 5 times x plus 3 over x minus 5, and I can cancel that x minus 5 in the numerator denominator, and I really have the function f of x is x plus 3 so long as x is never equal to 5. That's the function that you see graphed. Well, in addition, we can go ahead and add a little bit of clarity. We can say, what happens if we approach a from either the left or the right? So take a look at the graph of this function, whose piecewise equation is sitting up in the top right corner of the screen. A left-hand limit as f of this function f as x approaches a, in this case a is 2, is denoted by putting a superscript right there above that value of a. That equals L, so let's go ahead and trace along the graph and approach 2. We're getting very close to some output. So long as we can get as close to L as we'd like, in this case it's 4, as close to 4 as we like, we just have to be sufficiently near A, sufficiently near 2. And again, we don't care what happens at 2. So what we would write here for our notation is we would say the limit as x approaches that input value 2 from the left, that would be equal to 4, because we're getting very close to the output of 4. Now what I want to do is take a look at approaching 2 from the other side, from the right. So now as I approach 2 from the right, take a look at the branch just right of 2, where our inputs are greater than 2. Notice what happens. We're getting very close to a different output value. We're getting very close to 8. So the way we would denote this is we would say the limit as x approaches 2 from the right, and I'd use a superscript of a plus sign to show that, that's going to be equal to 8. And the definition says, well, we can get as close to L as we like. We just have to take values of x that are greater than a, but close to a. And again, we don't care about what happens at a. So when we take a look at these two graphs, we can kind of put the two thoughts together and say, when I write down that the limit of a function exists, and that's my two-sided limit, as x approaches a, means I'm approaching from both the left and right side, what must happen is that the left-hand limit of the function must equal the right-hand limit of the function. Now, when I take a look at the graph on the left for this particular function, notice, if you will, if I was to write this out, I would say the limit as x approaches 5 of f of x is equal to 8. And that's because my left-hand limit as x approaches 5 is 8, and my right-hand limit as x approaches 5 is 8. When I take a look at the graph on the right, my limit as x approaches that input value of a 2, well, let me pause for a sec. The left-hand limit as I approach 2 was 4, and my right-hand limit as I approach 2 was 8, and those two values are not equal. So now I would say my limit does not exist, and I'd use the abbreviation DNE. Thank you. Let's take a look at the limit as x approaches 2 from the left. So I'll put a superscript of a subtraction symbol to show that, of this function f of x, and we're approaching from the left. So when x is approaching 2, nearing 2, and it's from the left, that means the values of x are smaller than 2. Now near 2, we'll look at the corresponding part on the graph and notice the outputs are getting very close to 8. So the limit, left-hand limit as x approaches 2 is 8. Now let's take a look at the limit as x approaches 2 from the right. So we'll use a superscript of a plus sign to designate that x is approaching 2 from the right. When x is approaching 2 from the right, this means x is greater than 2 but very near 2. We'll look at the corresponding part of the graph and notice that as x nears 2, those outputs are getting very close to 3. So the right-hand limit as x approaches 2 of this function is 3. Now we'll look at the two-sided limit. The limit as x approaches 2 of f of x means we're looking at the two-sided limit. And for the two-sided limit to exist, the left-hand limit and the right-hand limit must be equal. But notice, they're not equal. So this means my two-sided limit as x approaches 2 does not exist, so I'll use the abbreviation DNE. Lastly, let's look at the function value f of 2. So this means when x equals 2, what is the y-coordinate? Well, notice right here we have the point on the graph of 2, 3, and the y-coordinate is 3, so f of 2 is 3. Estimate finite limits or one-sided limits at given values using tables. Here's our goal. We want to be able to estimate the limit of a function as x approaches a, so we're approaching a from both the left side and the right side. And the way we're going to do this is numerically by setting up a table. So how do we do this? Well, when we create the table of values, the inputs of values of x that are near a but approaching from the left will be written down. And so these values will be less than a. The inputs of x that are near a but approach a from the right will also be written down. And again, these values will be x values that are, in this case, greater than a. Now, we're going to ask ourselves if the output values from the left and from the right get closer and closer to the exact same number. And if they do, you know what? That's the limit. But if they don't get closer to the same number, we say the limit does not exist. So, here's our function. Our function is f of x is equal to x cubed minus 125 over x minus 5. We got to ask ourselves, well, what is a? Well, we're approaching 5 from the left and the right side. And notice that if we substitute a 5 into our function, our denominator is 0. So what we're going to do is we're going to allow ourselves to put in values of x that are going to approach 5 first from the left. So these values of x right here are representing values that were approaching 5 from the left, and I use a superscript of a minus sign or a negative sign to show that. And we're going to see if those outputs, and so I'm going to go ahead and say, are these numbers approaching some value? And if they are, what do we write? Well, what we write is that the limit as x approaches 5 from the left of the function would be equal to that value. Now stay with me on this. Next, we're going to approach 5, but from the other side of 5, with values that are greater than 5. So we're going to approach from the right. So as I near 5, it's strange, but I'm actually getting closer as I go from right to left, if that makes sense. And these values are approaching 5 from the right, so we write x approaches 5, and we put a superscript of a plus sign to denote that we're approaching from the right. And again, we're asking ourselves a very basic question, ladies and gentlemen, which is, are those outputs approaching a value? And if they are, then we would write the limit as x approaches 5 from the right of this function would be equal to some number. Now, to answer the question, I'd sure like to know if those two numbers are the same. Because if those two numbers are the same, we'd go ahead and use that for the answer. Now that we have it all set up, this is what you do. You go to the table feature, and it's the fastest way of doing this. You use this table feature where you can input values of x. So put the function into your graphing calculator. You would enter it as x to the third minus 125 divided by x minus 5. Then go to the table feature and set it so that you can input values of x. And you would input the values of 4.9, 4.99, and 4.999. Now I'm going to round here to, well actually I won't need to round, but I'm going to go ahead and put down what those outputs are. So for 4.9 the output is 73.51, and for 4.99 the output is 74.8501. And then for 4.999, the output is 74.85 and then 001. So when I look at those outputs, as I go from an input of 4.9 all the way through 4.999, those outputs seem like they're getting closer and closer to 75. So that's my left-hand limit as I approach 5. For my right-hand limit, again, I'm going to put in values that are greater than 5. And I'm going to put in 5.1, which is about as far away as this table allows me to be. I'll get closer to 5 by putting in 5.01. Well, that gives me 75.1501. And then 5.001, now I'm really close to 5. That output is 75.015001. And again, I'm asking myself, as my inputs go from 5.1 to 5.001, are those outputs getting closer and closer to a number? And your response is, I believe so. It looks like it's getting closer to 75. So my right-hand limit as I approach 5 is 75. Then I ask myself the only question that really matters in my entire life, which is the left and right-hand limits equal? And they are. So that means when I come back to the question, which is right here, ladies and gentlemen, my two-sided limit as I approach 5 is that 75. And for my very last sentence, if those two limits, the left and right-hand limits, would not equal, we would say that limit as I approach 5 does not exist. But here it does. Thank you. Let's numerically estimate the limit shown below by setting up a table of values. It's the limit as x approaches 0 of 5 sine x over 3x. Make sure your calculator is in radian mode and that the settings are such so that you can enter values in the input or x column on the table feature. So what I'm going to do is set up a table. I'm going to allow my inputs to be x and my outputs to be f of x. And I'm going to choose 3 values left of 0, but each one successively nearer to 0. I'm going to place those values on my table. Then I'll have 0, and I know if I substitute a 0 into the function, the result is that we're going to be dealing with an undefined output. Then I'll choose 3 values right of 0, each one, as I move to the right, successively closer to 0. So when I choose these 3 values right here, what I'm doing is I'm exploring the left-hand limit as x approaches 0 from the left of f of x. And whatever I get, I'll place right here. When I go ahead and approach 0 from the right, I'm going to again look at exploring the right-hand limit. The limit as x approaches 0 from the right. And what I'll do is I'll put that value right here. Now, if the left and right-hand limits are both 0, that will be my two-sided limit. And that two-sided limit, well, I'll put that right here. So for my left-hand limit, I'm going to start by choosing an input of negative 0.1, then move closer to 0, negative 0.01, and then negative 0.001. And I have three values such that x is less than 0. Now for my right-hand limit, I'll choose values of x that are greater than 0. And I'll start with 0.1, and then I'll near 0. I'll get even closer, 0.01. And then even closer, 0.001. And what I want to do is look at the corresponding outputs. So I'll enter my function into my calculator. I'll turn to the table feature, enter each of these inputs, and read off the outputs right off of the table feature. And I'll round to 5 decimal places. For the input of negative 0.1, I end up with 1.66389. So I'll write that into my table. And again, we're rounding to 5 decimal places. For my next input of negative 0.01, rounded to 5 decimal places, my output is 1.66664. And for negative 0.001, my output is 1.66667. Now, what I want to do is see if I can estimate the left-hand limit as x approaches 0 from the left. So what I'm asking myself is, what number are these outputs approaching? And it looks like they're approaching 1.6 repeating, which I'll write as 5/3 exactly. Now let's explore the right-hand limit. When x is 0.1, my output is 1.66389. So I'll write that into the table. When x is 0.01, my output is 1.66664. And when x is 0.001, my output is 1.66667. And again, we're trying to determine what number we're approaching as x approaches 0 from the right. It sure looks like those outputs are approaching 1.6 repeating, which is 5/3. So I'm going to ask myself, is my left-hand limit equal to my right-hand limit? And it is. So my two-sided limit as x approaches 0 of 5 sine x over 3x is 5/3. Use technology to estimate limits. We want to use technology to estimate limits. And one nice way of doing it is with a table of values, in which the input values of x approach from both the left and right sides, depending upon the limit that's requested, or even both. And then, in turn, we determine if the output values are getting closer and closer to some real value L. We're going to look at two problems, and they're as different as night and day. In the first problem, what we want to do is approach 3. That means we're approaching from both the left and the right-hand side. Now, if I put a 3 into the function, my denominator is 0. So the first thing I notice is that as I approach 3, at 3, my function is undefined, which is neither here nor there, because the very concept of a limit says what happens when we near 3, get as close as 3 as possible from the left and the right. Let's start from the left. As x approaches 3 from the left, I'm going to put in values that are smaller than 3, but nearing 3. So this is where we're approaching 3 from the left. And we're asking ourselves a very basic question, which is, do the corresponding outputs approach a value? And if they do, what I would do is I would write the limit as x approaches 3 from the left of this function is equal to that value. And then I'm going to go ahead and approach 3 by taking values of 3 that are very near 3, but larger than it. I'm going to approach 3 from the right. So here we're approaching 3 from the right. And we're asking the same question, which is, what is the limit as x approaches 3 from the right of this function? And once we find the left-hand, right-hand limits, we'll see if they're equal. And if they're equal, then that will be the answer to our question. So if they're equal, we'll go ahead and just put that answer right there. So what I would do is I would go into the table feature. So I would enter my function in y1 and go to the table feature and enter the values of the inputs to be 2.9, 2.99, and 2.999. And when you do, here are the corresponding outputs. Corresponding outputs are 0.4, 0.49, and 0.499. And as x goes from 2.9 to 2.999, those outputs are getting closer and closer to 0.5. So I conclude that is my left-hand limit of this function as x approaches 3. Similarly, I go back to my table feature and I enter values of 3.1, 3.01, and 3.001, and the corresponding outputs as I get closer are 0.6, I'm just reading this off the table, 0.51, and off the table in my calculator I see 0.501, and as x gets closer to 3 from the right, as the values go from 3.1 to 3.001, it sure looks like that those outputs are getting closer to 0.5 as well. Is the left and right hand limits equal? You betcha. I'm sorry for the strong words, but it deserves it. So that means my two-sided limit as I approach 3 is 0.5. Now that's it, almost. Almost, because in the second problem we see a little bit of a twist. Same exact scenario. We have the limit as x approaches a number, in this case it's 0, of a function. In this case it's the sine of 10 over x. So again, I'm going to use the table feature. Again, I'm going to put the function into y1. But here I just want to pause and say, make sure you're in what? You're in what? You're in radian mode. And then I'm going to put in values that are approaching 0 from the left and right, but again, notice that at 0 my function is undefined because my denominator of my argument is 0. So, as I approach 0 from the left, and that's what we're seeing right here, x is approaching 0 from the left, we're asking ourselves a very fundamental question, which is, gosh, are these values here approaching a number? And if they are, then we're going to say then the limit, the left-hand limit as x approaches 0 of the function would be equal to that value. And you probably know what I'm going to sketch here. I'm going to say then we're going to approach 0 with values that are greater than 0. We'll approach from the right. X is approaching from the right. We'll use this notation. And we'll ask ourselves again that question, what is the limit as x approaches 0 from the right of this function? And if I can find that value, I'll put it here. And again, if these two numbers are what? Are equal, then that would be the answer to our question right up here. Now, off of the table feature in the calculator, I'm going to write in these corresponding outputs, which is 0.5064, negative 0.8269, and 0.3056. And it sure does not look like I have a left-hand limit. Those outputs don't seem to be nearing anything at all. In fact, I would like to conclude that my left-hand limit as I approach 0 does not exist. That in and of itself tells me my answer does not exist for my two-sided limit. Now, if I did choose to look at the right-hand limit, because sine is an odd function, then when I take a look at the value of the sine of 10 over x at 0.1, it would just be the opposite sign of what I just had, negative 0.5064. And then my output at 0.1 would be positive 0.8269. And my value, output value at 0.001 would be negative 0.3056. But ladies and gentlemen, I come to the same conclusion, that my right-sided limit does not exist as well. So when I use technology here, I find the limit as I approach 0 does not exist. Thank you. With the use of a graphing utility, if possible, determine the left and right-hand limits of the following function as x approaches 0. And the function we have is f of x is equal to 3 times the sine of pi over x. If the function has a limit as x approaches 0, state it. And if not, discuss why there is no limit. Now, before we begin, make sure your calculator is set to radian mode. And what we'll do is we'll look at exploring these three limits graphically. So go into your graphing feature and enter your function 3 times the sine of pi over x. And let's first graph the function on a domain of -2 to 2 so that we're near 0. And when we do, if we go ahead and allow the calculator to set the range, or we can, the range would be from -3 to 3, because we know sine is bounded from -1 to 1, and if you multiply it by 3, now sine is bounded from -3 to 3. But the graph you end up getting shows some oscillation as I near 0. Now I'm going to sketch this oscillation as I near 0, and notice that I'm oscillating between -3 to 3, and what I can't tell is if the graph goes through the origin or if the graph approaches some other value. So I'm going to now change the domain so I'm truly near 0. I'm going to change the domain that I graph so that I'll graph between -0.1 to 0.1. And again, when I do this, I'll label on my x-axis -0.1 to 0.1, and again on the y-axis, I know the outputs will go between -3 and 3. But now as I explore the graph, I see the same oscillation. The graph almost seems to be oscillating from -3 to 3 in the same way it did a moment ago. So I'm going to think to myself as x approaches 0 that perhaps this function does not exist. I don't get close to a single output. If I was to graph it again and be even nearer to 0, just to reassure myself, from -0.01 to 0.01, and again I mark along my axis from -0.01 to positive 0.01, again I know the range will go from -3 to 3, I would think that if I did have a limit, I'd be able to see these functional values approach some output. But again, I see the same oscillation that I witnessed before. So as I near 0, I know that my left-hand and right-hand limits both don't exist. So let's go ahead and answer our question. What is the limit as x approaches 0 from the left of this function? Well, that would be does not exist. And what would be the limit as x approaches 0 from the right of this function? Again, that would be does not exist. And our two-sided limit as x approaches 0 for a function as well does not exist. Evaluate limits or one-sided limits if they exist using limit properties. There are properties that we can use to evaluate limits that make these evaluations quick because we're just doing algebra. Now, I know there's a whole lot here to absorb, and you're welcome to look through these limit properties, but let's go ahead and just explore a couple of them and take a look at what they're saying. The first one is we want to take a look at the limit as x approaches 10 of 3x squared plus 4. So what we can do is we can go ahead and say, gosh, I can take a look at the limit of a sum and write it as a sum of the limits. So I have the limit as x approaches 10 of 3x squared plus the limit as x approaches 4 of the constant, of x approaches 10, of the constant function 4. Then I have a constant times x squared, and so my limit as x approaches x squared times 3 would be the same as the limit as x approaches 10 of the 3x squared. That enables me to bring that 3 out front. So now I have the limit as x approaches 10 of x squared, plus the limit as x approaches 10 of the constant function 4. Well, imagine the parabola y equals x squared. And ask yourself, when the inputs get close to 10, those outputs get close to 10 squared, because you're getting close to the point 10 comma 100. So we say we can evaluate directly. So now we have 3 times 10 squared plus, imagine the line y equals 4. That's the constant function. When x is approaching 10, we're getting close to 10. But every single output on that function is 4. So the limit would be 4. And we end up with 3 times 100 plus 4, or 304 as our result. So another way of phrasing this is when we can evaluate directly with these limits, we do so. Well, that was well timed, because I want to evaluate the limit of this function as x approaches 3. But if I substitute a 3 into the function, what happens? My denominator is 0. So I have to algebraically manipulate the function. And I can do that by factoring the numerator and denominator. But I want to keep the limit symbols until I evaluate, because if I don't, I'm implying that I can substitute a 3 into the function. And remember, and this is what's key, when you write the limit as x approaches 3, this means you're near 3, but not at 3. So I can put in values, therefore, into the function very close to 3. What I can't do is put in the number 3. So I keep the limit symbols for that reason. Now, you may say to yourself, I don't want to factor the numerator, it's messy. So factor the denominator first. I can factor out the 2, that's easier. That leaves x minus 3. And if we do get a cancellation of factors, that means the x minus 3 would factor. So I'm going to try x minus 3 as one of the factors of the numerator. And I can then very quickly figure out the other factor. X times 2x is 2x squared. And negative 3 times negative 5 is 15, positive 15. And now my middle terms add up to negative 11. Now notice the x minus 3's cancel. So the result is that I have the limit as x approaches 3 of 2x minus 5 divided by 2. And what can I do? I can now substitute in and evaluate directly. I can put in a 3 for x. So if I do that, I end up with 2 times 3 minus 5 over 2. And I drop the limit symbols because I am putting a 3 into my function now. Well, 2 times 3 is 6, minus 5 is 1. I guess my limit is 1/2. Other ways to manipulate functions. Here I can't put a negative 6 into the first function I see because my denominator is 0. So what I want to do is see if I can go ahead and rearrange this complex fraction. So I'm going to multiply both the numerator and denominator by 6x over 6x, which is like multiplying by 1. And then I'll see if I can get any cancellations. And try this on your own. When you do, I'll put the answer down. You end up with, I'll go dot, dot, dot after a series of steps, negative 1 over 72. You can verify that. In the second problem, I can't put a 0 into the function because the denominator is 0. So here we want to try to multiply the numerator and denominator by the same exact expression and try the conjugate of the numerator. Multiply both the numerator and denominator by the square root of 36 minus x plus 6. And after some manipulation, you'll get some terms to cancel. And to check yourself, the answer here would be negative 1/12. Thank you. Let's evaluate the limit shown below algebraically. We have the limit as x approaches 2 of the rational function x squared minus 6x plus 8 over x minus 2. Our first thought process is to see if we can evaluate directly, but we can't because we would end up having a denominator forced to be 0. So our goal is to somehow rewrite the function to get that x minus 2 factor in the denominator to cancel with a common factor in the numerator. So I'll write the limit as x approaches 2. And what I'm going to do is factor the numerator. So to factor the numerator, I need numbers that would multiply to 8 and subtract away to negative 6. So I would have x minus 2 times x minus 4. And in the denominator, I have still x minus 2. Now notice, I have not gone ahead and drop my limit symbols, I don't do that until I actually evaluate the limit. So my next step is to cancel the common factors. What would that leave us? That would leave us the limit as x approaches 2 of x minus 4. And with the two terms, you do need them inside the parentheses. Now at this point, ask yourself, can you go ahead and evaluate directly? Can I substitute a 2 in for x? And the answer is absolutely. So at the point you evaluate directly, you can drop the limit symbols, and so the limit would be equal to 2 minus 4, and that is negative 2. Let's evaluate the limit as x approaches 5 of 1 over x minus 1 over 5 divided by x minus 5. Well, our first step is to always try to evaluate directly, but here the denominator would be a 0. So if I go ahead and start, I'm going to say to myself, let me rearrange this function, and I'm looking really right here in the numerator, to see if I can somehow create a factor of x minus 5 so I can cancel with this x minus 5 in the denominator. So I'm going to write the limit as x approaches 5 of 1 over x minus 1 over 5 all over x minus 5. And I'm going to multiply the numerator by the least common denominator, which is 5x. Because again, what I'm trying to do is create a factor of x minus 5. I'm trying to change the form of my numerator. So I'll have the limit as x approaches 5. And I'll have 1 over x minus 1 over 5 over x minus 5. And if I'm going to multiply by 5x, which is the least common denominator in the numerator, what else do I have to do? Multiply by 5x to the terms in the denominator, because then I'm really going ahead and multiplying through by 1 and not changing the value of the expression. Now notice, in the numerator, we have 5x times 1 over x, and that's 5. We also have 5x times 1 over 5, and that would be just x. So my next step is to write down the result of that multiplication. So I have the limit as x approaches 5, and the first term would be what? It would be 5 minus the second term would be what? It would be x. And in the denominator, I have 5x times x minus 5. And again, until I actually evaluate the limit, I keep the limit symbols. What I'm doing is I'm checking to see if I can go ahead and cancel this factor of x minus 5. So I'm looking for a common factor of x minus 5 in the numerator. And I have 5 minus x. But I do know that if I factor out a negative 1 from 5 minus x, I end up with negative 5 plus x. And that's the same as what? Negative x minus 5. So that's my strategy. I'll go ahead and again write the limit symbols. The limit as x approaches 5. And in the numerator, I'll factor out that negative 1. That would leave me x minus 5. And in the denominator, I have 5x. X minus 5. And now I have that cancellation I was looking for. I can cancel the x minus 5 in the numerator and denominator. What does that leave me? Well, it leaves me the limit as x approaches 5 of negative 1 over 5x. Now I can go ahead and substitute in a 5 for x, and my denominator won't be 0. So what does this leave me? Well, this leaves me negative 1 over 5 times 5. So it looks like my limit will be negative 1 over 25. Let's evaluate the limits shown below algebraically. We have the limit as x approaches 0 of the quantity square root of 25 minus x minus 5 divided by x. Now if I try to evaluate directly, Notice that if I substitute in a 0 for x, we'll divide by 0, so we cannot evaluate directly. So what I want to do is perform some algebra so I can cancel out that x. And if I look at the numerator, the only x that I see is sitting inside of a square root. So I'm going to multiply the numerator and denominator by the conjugate of the numerator. And the reason I'm doing this is to try to get this x that I'm seeing out of the square root to cancel with the x in the denominator. So I have the limit as x approaches 0 of 25 minus x minus 5 over x. I'm going to multiply this by the conjugate of the numerator on both the numerator and denominator. And I'll take the limit of the whole result. So I'll multiply the numerator and denominator by the square root of 25 minus x plus 5 over the square root of 25 minus x plus 5. And to multiply by the conjugate, just to remind you, all I did was change the sign of the second term. Now take a look at the numerator. Are you seeing a minus b times a plus b is equal to a squared minus b squared? Are you seeing the square root of 25 minus x minus 5 times the square root of 25 minus x plus 5 as being equal to the first term squared, which is 25 minus x minus the second term squared minus 25. This is equal to the limit as x approaches 0. And in the numerator, what did we end up finding out? We had 25 minus x minus 25. And in the denominator, we had x times, well, we have the square root of 25 minus x plus 5. Now, our focus to remind you is that we're trying to cancel what? We're trying to cancel the x. Notice 25 minus 25, well, that's 0. So in my next step here, I'll take the limit as x approaches 0, and I'll write my numerator, but my numerator is just negative x. And that's divided by the factor x times this other factor, which is the 25 minus x inside the square root plus 5. Well, because x is a factor in the numerator and denominator, I'll be able to cancel them. And being careful to keep my limit symbols until I actually evaluate, one more time I'll write the limit as x approaches 0, and what's left in the numerator? Well, I've canceled the x, so it looks like we just have a negative 1. What's left in the denominator? We've canceled the x. We have the square root of 25 minus x plus 5. Are we able to now substitute in a 0 for x? And the answer is yes. So at the point we evaluate, we may drop the limit symbols. In the numerator, we're left with negative 1. And in the denominator, we're left with 25 minus 0 inside of the square root plus 5. So now we have this equal to negative 1 all over the square root of 25 plus 5, which is all over 5 plus 5, which is 10. Looks like our limit as x approaches 0 for this function is negative 1/10. Use the definition of continuity to determine continuity of functions at given values. A continuous at a point means basically, if you're in pre-calculus, that you can draw your pencil through that point, continue on the other side without lifting that pencil from the paper. But in calculus, we are very specific. We talk about why a function cannot be continuous at a point. And to do that, we have to define what it means to be continuous at a point, like x equals a. So if I'm at x equals a, and I'll put an a right here, if I'm continuous at x equals a, 3 different criteria have to hold. The first is that there has to be a point at a. So f of a has to exist. So there has to be a point there, and f of a has to exist. And so make believe f of a is, say, 10. Now the next thing that has to happen is that the two-sided limit as you approach a has to exist. So as I approach a from the left and the right, I'm zeroing in at the same point, and those outputs are the same as I approach from the left and the right. So if I go ahead and just imagine this value to be a 3 and put an open circle here, so I approach a from the left and the right, it doesn't matter because my output I'm approaching is still 3. Now you must be thinking something's terribly wrong because this function is not continuous at a. And that's the point I'm trying to make. The very last criteria says that this point we're defined at has to be moved into that circle. So we say that our limit as x approaches a must equal f of a. And if that's the case, and if I color it in this circle and remove that one, my function would be continuous at a. If a function is not continuous at a, we say it's discontinuous at a. Take a look at this function. It's a piecewise function. Let's see if this function is continuous at 3. That's what I want to know. So I'm going to go ahead and just underline the 3. That's what we have. And the first thing I want to know is, does f of 3 exist? So I'm going to write down f of 3. But when I take a look at my piecewise function, I'm never defined at 3. So f of 3 does not exist. There is no point at x equals 3. Well, stop. My function is discontinuous at x equals 3. I don't need to go any further. Is the function continuous at 3? No. No. Take a look at the next piecewise function. And again, we want to know, are we continuous where? Are we continuous at 3? So, is my function defined at 3? What is f of 3? I'm going to write 1. This is our first criteria. F of 3, well, the equal sign is here. We'll use this function. That'd be 3 squared, which is 9. So the first criteria absolutely holds. For the second criteria, does the two-sided limit hold? So the first thing I'm going to do is ask myself, what is the left-hand limit as I approach 3? So I'll mark that with 3 in a superscript of this function. And I want to choose to put in values of 3 that are smaller than 3. All right, that places me right here, right there. Well, it will near where 3 is on the function x squared. And so this would be 9, my left-hand limit as I approach 3. For my right-hand limit as I approach 3, I'm going to put in values of 3 that are now greater than 3. So now I'm looking at using x greater than 3 as the domain that I'm focused on, and the function I'll use is x plus 4. So when I take a look at this limit, right-hand limit as I approach 3 from the right, the calculation would be 3 plus 4, which is 7. And is my left-hand limit equal to my right-hand limit? Well, my left-hand limit as I approach 3 is a 9. My right-hand limit as I approach 3 is a 7. Absolutely not. So since they're not equal to, this particular second criteria fails. So we're discontinuous at 3. Is my function continuous at 3? No, no. Well, let's take a look at our third function. Does f of 3 exist? Because we're still asking that same question. Are we continuous at 3? Well, does f of 3 exist? Let me write down f of 3. At x equals 3, the output's 7. It absolutely exists. Does my two-sided limit exist? Well, let's go ahead and check that out. As I look at the limit as x approaches 3 from the left, I'm using values of 3 that are less than 3. So I'm dealing with the function x squared, and that left-hand limit is 9. When I take a look at the right-hand limit as x approaches 3 to see if I get back 9, I say to myself, all right, well, goodness, I'm putting in values of 3 that are more, or I'm putting in values of x that are more than 3. I'll use the function x plus 6. And 3 plus 6, well, that is 9. So if I go ahead and say to myself, what is my two-sided limit? The limit as x approaches 3 of this function, that would be 9. The left and right-hand limits are equal. So the only thing I have to do is double-check does my output at 3 equal my limit at 3? Well, the limit as x approaches 3 of this particular function is 9, and the function value at 3 is 7. Yeah, I don't think they're equal. So because the third criteria breaks down, again, we're discontinuous at x equals 3, and the answer to our question is no, we're not continuous at 3. Thank you. Determine points and types of discontinuities of given functions. Now, we know what it means for a function to be continuous at x equals a. F of a has to exist. The two-sided limit as x approaches a of the function has to exist. And that two-sided limit has to equal f of a. But here's the thing. What we want to do is look at 3 ways a function could be discontinuous at x equals a. So our focus will be right here. What are 3 common discontinuities? For the first one, we're just simply going to graph this particular function to look at it. So we have this parabola when we're left of x equals 1. And it has a vertex of 1, 2. And it goes through the point 0, 3. And actually at 1, 2 should have an open circle right there. So I'm going to place that. And I'll sketch that parabola. Now, at x equals 1 and to the right of it, we have the function y equals 4x. So I'll go ahead and go to the point 1, 4 and try to sketch a line of slope 4. Now, when I approach 1 from the left and the right, clearly my limits don't match up. In fact, if I was on the left branch, when I got to x equals 1, I'd have to kind of jump up to the right branch. So what I'm saying is that if I take a look at the left-hand limit as x approaches 1, I see that that would be 2. And the right-hand limit as x approaches 1, well, that would be 4. So when we have the limit as I approach from the left existing, but not equal to the limit as I approach from the right, this type of discontinuity is called a jump discontinuity. Because students remember to get from one branch to the other at that point of discontinuity, you kind of have to jump over to it. So we have a jump discontinuity at x equals a. For the second discontinuity, what we're going to do is take a look at a parabola again. It's the same parabola we had a moment ago. It's just that now this parabola is defined everywhere but at 1. And at 1, well, the output is 4. And it almost seems like we've removed a point from the parabola. These type of discontinuities look something like this. If I take a look at the two-sided limit as I approach 1 of this function, that would be 2. But the function value at 1 is different. That would be 4. So whenever we have a case where we have our two-sided limit as x approaches a of a function existing but not equal to the function value at a, this is called a removable discontinuity at x equals a. And students remember that they basically are just removing a point. They kind of have a hole in the graph at x equals a. For a third type of discontinuity, we're taking a look at f of x is equal to 1 over x minus 1. And so we know what this function looks like. It's basically our function of 1 over x that's been shifted to the right 1 unit. And I notice that when I take a look at the limit as x approaches 1 from the left, since that branch is going down, it would be negative infinity. And when I take a look at the limit as x approaches 1 from the right, well, as I near 1 from the right, the branch is going up. It's shooting to positive infinity. This type of discontinuity where you have asymptotes are called infinite discontinuities at x equals a. And this will occur when either the left-hand limit as I approach the function is equal to either infinity or negative infinity, or the right-hand limit of this function as x approaches a is infinity or negative infinity. Thank you. Let's identify all discontinuities for the following functions as either jump or removable discontinuities. The first function is f of x is equal to x squared minus 2x minus 15 over x minus 5. So we do know that we have a discontinuity at x equals 5 because that forces the denominator to be 0. Now the question is it a jump or removable discontinuity? Well, let's see what we know about this function. We know f of 5 does not exist. And we also know that if we took the limit as x approaches 5 of this function, which again is x squared minus 2x minus 15 over x minus 5, then we would go ahead and find that the two-sided limit does exist. If I go to factor the numerator, I have x minus 5 times x plus 3. And because I have a common factor in the numerator and denominator, I can go ahead and cancel those factors. So when I evaluate the limit, I now am evaluating the limit as x approaches 5 of x plus 3. And that's just equal to 8. Now I need you to picture, if you will, the graph of a line, and that line is y is equal to x plus 3, but you're removing 5 from the domain. What type of a discontinuity is this? This is a removable discontinuity. So I'm just going to write removable right here. Let's take a look at our second function, which is a piecewise function. We have f of x is equal to x plus 1 when x is less than 2, and negative x when x is greater than or equal to 2. Well, because each function that defines the piecewise function are functions whose graphs are lines, each individual function is continuous on their domain. So the only possible point you can have a discontinuity would be at 2. So we're going to explore x equals 2. And when we look at f of 2, because of this equal sign right here, we know we would use the equation negative x to evaluate f of 2. And we'd find f of 2 to be negative 2. So at the only point we can have the discontinuity, we do know f of 2 is defined. So next we'll go ahead and check the limit as x approaches 2. And if you're approaching 2, you're going to have to check the limit as x approaches 2 from the left, and you would use one function, and then from the right, and you would use another function. Well, if x is approaching 2 from the left, we're dealing with values of x that are smaller than 2, less than 2, so we'll use the function x plus 1. I can evaluate directly, so if I substitute in a 2 for x, I end up with a limit equal to 3. When I look at the right-hand limit as x approaches 2, I'm going ahead and choosing values of x that are greater than 2. I would use the function negative x. And again, I can evaluate directly. If I substituted a 2 in for x, I end up with negative 2. And now I ask myself, is the left and right-hand limits equal? And the answer is no, they're not equal at all. So that means my two-sided limit as x approaches 2 does not exist. So if I took the limit as x approaches 2 of f of x and realize it doesn't exist, but I do have the function defined at 2, I am picturing a jump, if you may. I'm picturing a jump where when I approach 2 from the left, I'm 3 units above the x-axis, and then when I go to the right of 2, I jump down 5 units to get to negative 2, 2 units below the x-axis. What am I driving at? What type of discontinuity do we have? a jump discontinuity. Let's determine whether the function shown, which is f of x is equal to x squared minus 25 over x minus 5, is continuous at x equals 5. So to determine if a function is continuous at x equals 5, we'll determine if the three conditions of continuity are all satisfied at x equals 5. If any of the conditions are violated, well, the function is discontinuous at x equals 5. Let's take a look at condition 1. For condition 1, we'll ask ourselves, does f of 5 exist? Is the function defined at x equals 5? Well, notice if I substitute a 5 into the function, well, the denominator is 0, and so f of 5 does not exist. I'll write DNE for that. Now, there is no need to proceed any further. If any of these conditions fail, well, we know we do not have continuity at the specified location. Well, let's answer the question. Determine whether the function shown is continuous at x equals 5. Looks like our function f is not continuous at x equals 5. And why do we know this? Well, this is because condition 1 fails. Let's determine whether the function f is discontinuous at any real numbers. F of x is equal to x plus 1. If x is less than 2, it's equal to 3. If 2 is less than or equal to x, which is less than 4, and it's equal to x squared minus 11, if x is greater than or equal to 4. Now, those three functions that make up my piecewise function that are underlined, they are all polynomials. I have two lines and a parabola. Well, graphs of these functions are continuous everywhere on their domains. So the only possible places I can have discontinuities is at the boundary points. And the boundary points would be at 2 and at 4. So for each of these points, and I'll just refer to them generally as x equals a, I'm going to ask three questions. Does f of a exist? And does the limit as x approaches a of the function exist? And lastly, is f of a equal to this two-sided limit as x approaches a of f of x? And if all three of the criteria hold, well, at x equals a, we have continuity. If not, we can say the function is discontinuous there. So the first boundary point we'll explore is at x equals 2. We're going to ask, does f of 2 exist? Well, because of this inequality symbol, I know that when x equals 2, I'll use the middle function, and f of 2 is 3. So yes, f of 2 does exist. Let's take a look at the limit as x approaches 2 of this function. I'll start by looking at the left-hand limit as x approaches 2 of the function. If I'm looking at the left-hand limit, I'm choosing values of x that are less than 2. Well, that places me in the first function. So I have the limit as x approaches 2 from the left of x plus 1. What is that limit? Well, I can evaluate directly. It looks like that limit is 3. Let's take a look at the right-hand limit as x approaches 2. The limit as x approaches 2 from the right means x is greater than 2. I'll use the second function. So I have the limit as x approaches 2 from the right of 3. And that's just the constant function y equals 3, or f of x equals 3. So the output is 3. Since the left-hand limit and the right-hand limit are equal, this tells me my two-sided limit as x approaches 2 of this function is also 3. Well, f of a exists. The limit as x approaches a of f of x exists. Now we have to ask ourselves, is f of a equal to the limit as x approaches a. In this case, a is 2. And the answer is absolutely. We know that f of 2 is equal to the limit as x approaches 2 of f of x. All right, so that means that at x equals 2, the graph is continuous. So if I'm answering this question accurately, determine whether the function is discontinuous for any real numbers, now I'm down to the only possible real number it can be discontinuous at is 4. So I'll go ahead and look at starting with asking myself, does f of 4 exist? Well, if I look at this inequality symbol, I know to use the third equation when evaluating this function at 4. And when I do that, I end up with 4 squared minus 11, which is 16 minus 11, that's 5. So f of 4 does exist. Now how about the two-sided limit as x approaches 4? Well, let's take a look at the left-hand limit. If I take a look at the left-hand limit, I have the limit as x approaches 4 from the left. I'm dealing with choosing values that are smaller than 4, less than 4. I'll use the middle equation. That output is always 3. And when I look at the right-hand limit as x approaches 4, I'll choose values that are greater than 4. That means I will choose the third equation to evaluate that limit. So that would be equal to the limit as x approaches 4 from the right. And I have x squared minus 11. Well, if I evaluate directly, I did that calculation a moment ago, the result is 5. Notice the left-hand limit as I approach 4 of f of x is 3, and the right-hand limit as I approach 4 of f of x is 5. Left and right-hand limits are not equal. So what this tells me is my two-sided limit does not exist. So going back to the question, determine whether the function is discontinuous for any real numbers. Yes, it is discontinuous. Where is it discontinuous? It's discontinuous at x equals 4. Why? Because the two-sided limit as x approaches 4 does not exist. Estimate slopes of tangent lines to graphs at given points. Our goal here is to estimate the slope of the tangent line to the graph at each of the 3 points we see highlighted and focus on the notation of how we write it. So we'll start at x equals 1, and it sure looks like that tangent line we see would be horizontal. And the slope of a horizontal line, well, we know what that is. That's going to be 0. So we would write the derivative at 1 is 0. Now when I go over to x equals 2 and I sketch the slope there, what I'll do, or sketch the tangent line there to approximate the slope, is sketch a tangent line. And when I do, I got to figure out the slope of this line. And it looks like I've gone right 1 unit, up 2 units. So the slope would be change of output over change of input would be 2. So my derivative at x equals 2 is 2. Now the third point is at x equals 3. Again, I'm going to sketch a tangent line. So to sketch a tangent line, I'm going to go ahead and do my best to create that tangent line, and to figure out the slope, I realize I've gone right 1 unit. Looks like I've gone up 4. And so my slope, rise over 1, would be 4. And I would write my derivative at 3 is equal to 4. Thank you. Find slopes of tangent lines using a limit definition. The derivative of a function could be interpreted as follows. It could be considered the slope of the tangent line to the curve at A. So for any of these tangent lines, we'd go ahead and just figure out the slope. The derivative is written at x equals a, so that we're writing f with a little tick mark of a. And it measures how the curve changes at that point. And the limit definition that you see in front of you here is what we'll use to find that slope at a. So let's go ahead and give you a function and do just that. The function we give you is f of x is equal to 3x squared plus 5. And I want to find the slope of the tangent line to the graph of the function, or at least a function that will create those slopes for any input. And that's what the derivative is. It's that function itself. So the first thing I do is I say that the slope of the tangent line is going to be the derivative of the function. And I'll go ahead and evaluate this limit as h approaches 0 of f of x plus h minus f of x over h. Now to evaluate it, I'll again write in the limit as h approaches 0, and f of x plus h, well, that would be 3 times, instead of x, I would substitute in x plus h. So it would be 3 times x plus h squared plus 5, minus, and to make sure you're seeing where we are, that minus is this one right here, and minus the function. And the function is going to be 3x squared plus 5. So I need parentheses around both terms because I'm subtracting over h. Now if I can evaluate directly, I would do so, but I cannot substitute an h into my function, so I'm going to rearrange the terms by multiplying everything through to try to get a bunch of cancellations so I can eventually cancel the h out. Well, before I do this, I got to remember something, which is that x plus h squared is equal to x squared plus 2xh plus h squared. So if that's the case, in my next line, I'll write the limit as h approaches 0, and I'll multiply 3 by each of these terms right here. So that would give me 3x squared. 3 times 2xh is 6xh, and 3 times h squared is 3h squared, then plus 5, minus, and now I'm going to distribute through the parentheses. So minus 3x squared minus 5 over h. And you may be thinking I'm making things worse, but in reality I'm not. Because do you notice any cancellations that you'll get? 3x squared minus 3x squared is 0. 5 minus 5 is 0. And lo and behold, I'm left with 2 terms in the numerator, and each term has an h in it. I'm left with 6xh plus 3h squared over h. Now my goal is to cancel an h from the denominator, and I can do that, can't I? If I have the limit as h approaches 0, I can factor out an h in the numerator. That would leave 6x plus 3h. And now when I divide by h, do you see where the conversation is going? I can cancel these h's out. And that means, well, this well may be the best day of my entire life, because now I can evaluate h at 0. And if I substitute in a 0 for h, I can drop the limit symbols, and I end up with 6x. So that means my derivative, f of x, is 3x squared plus 5. Its derivative is 6x. So I can very quickly now figure out the slope of each of these lines. Let's start with the purple line here. The derivative at negative 2, well, remember my derivative function was what? My derivative function was 6x. So my derivative at negative 2, that would be 6 times negative 2, or negative 12. That's the slope of this line right here. How about the green tangent line? Well, the derivative at 0 would be 6 times 0, which is 0. And that's the slope of this horizontal line. That makes sense. Slopes of horizontal lines is 0. And the very last tangent line I see is here in blue, and we're looking at the tangent line at x equals 1. My derivative at x equals 1, well, that'd be 6 times 1, which is 6. Thank you. Find derivative functions using a limit definition. We're going to find a derivative function by taking a look first at an average rate of change between 2 points on a graph. One point is given by a, and if I go ahead and mark the point, the y-coordinate is f of a. Now the other point will be h units from a. Well, that would mark a plus h as the x-coordinate. And if I come up to the graph, the y-coordinate, well, that would be just f of a plus h. Now, the average rate of change between the 2 points is given by the slope of the secant line connecting those 2 points. And here's the concept. If I let h approach 0, get smaller and smaller, and so if I want to sketch a new value for h, and I'll do it in green, I'll let h now be smaller, then my new location of a plus h places a secant line that looks very different than the first secant line I drew. And the concept says if I allow h to approach 0, get very close, my 2 points, a and a plus h, get very close, then that secant line approximates the tangent line at a. And the slope of that tangent line is the slope of the curve at a. So that's what we're going to do. We're going to talk a little bit about the slope of the curve of the function, and this is really the rate of change at a particular instant. So if I go ahead and take any value of a, and I drew a tangent line there, the slope of that tangent line is approximately the slope of the curve at the point. Well, the way we write this function that gives these slopes of the curve at any point in the domain is f prime at a, and it's referred to as the derivative of the function at a. Now, the actual formula for it is found by taking the limit as h goes to 0, because that's what we really want to do, and we're looking at a change of output per change of input. Now let me show you what I mean. If I go ahead and just do what I did a moment ago, I'm going to allow one point here to be a, comma, f of a, and then I'm going to allow another point to be a plus h, comma, f of a plus h. What did we say we would do? Well, we said we would go ahead and let h go to 0. So the derivative at a would be the slope of the secant line connecting the 2 points. You say secant line. I say, yeah, secant line. It's right there. That's secant line right there. But if we allow h to go to 0, the slope of that secant line is just a slope. Change of output per change of input. Rise over 1. Rise over run, y2 minus y1 over x2 minus x1. You just subtract the outputs, f of a plus h, minus f of a, and subtract the inputs, which is a plus h minus a. And notice the a's cancel. And that's your limit definition of a derivative. And we refer to this as the limit of a difference quotient. So, interpretations, well, the derivative of the function at a single point is the slope of the tangent line at that point. It's written f prime of a, and it measures how the curve changes at that point. And it measures the instantaneous rate of change for the function at that point. As far as notations, how we write it, there's many ways to write it, ladies and gentlemen. I can go ahead and write the derivative. I can write y prime if the function's in terms of y. I can write change of y over change of x, dy dx, as h goes to 0 is what that implies. Or if the function is named in terms of f of x, df dx. All of these are notations for the derivative. Thank you. Let's determine the derivative of the function shown at x equals a. And the function is f of x equals x squared minus 3x plus 5. So I'm going to skip a space, and I'm going to write the derivative at a is the limit as h approaches 0 of f of a plus h minus f of a over h. Now, I know what f of a is. If I substitute a into the function f, I end up with a squared minus 3a plus 5. For f of a plus h, I'll substitute in a plus h everywhere I see an x. So this would be a plus h squared minus 3 times a plus h plus 5. So I'll substitute in f of a plus h here and substitute in f of a here. So the next line would read the limit as h approaches 0, and f of a plus h is a plus h squared minus 3 times a plus h plus 5. Then I'll subtract f of a, and we have 3 terms: a squared minus 3a plus 5 over h. Now I want to evaluate the limit, which means I want to substitute in for h a 0. And for the moment, I ask myself, can I do that? And the answer is no, I can't. So I'm going to multiply out all these terms, see if I can combine them, because I'm looking to cancel the h out of the denominator. So my next line would read, I have the limit as h approaches 0, a plus h times a plus h is a squared plus 2ah plus h squared. If I distribute the negative 3 through the parentheses, I end up with minus 3a minus 3h. Then I have plus 5. And then I'll distribute the negative 1 that I see out in front of a squared minus 3a plus 5. So I'll have minus a squared minus a negative plus 3a minus 5. And this is all over h. Now you may be thinking this is a very busy line, Jay. But to be honest with you, now my eye focuses for combining like terms, simplifying, for the hope of canceling that h when I'm looking at that simplified version. Well, what do I notice? I notice negative 3a and positive 3a cancel. What else do you see that cancels? Positive 5 and negative 5. Anything else? Right there in front of me, a squared and negative a squared. And notice, if my goal is to cancel the h, what I see is 1, 2, 3 terms left in the numerator, and they all have what? They all have an h. Do you see where I'm going with this? I'm going to factor out an h from the numerator to get my cancellations. So my next line is the limit as h approaches 0. And I'll write those 3 terms down, which are 2ah plus h squared minus 3h over h. And now comes that step I was talking to you about. I have the limit as h approaches 0, and I'll factor out an h from the numerator. From the first term, I have left a 2a. From the second term, an h. And from the third term, now I'm going to go ahead and subtract a 3. And because h is now a factor in both the numerator and denominator, what am I going to do? I'm going to cancel out those h's. Well, this is actually looking fabulous. Because if I write the limit as h approaches 0, and I take a look at the terms that remain, which is 2a plus h minus 3, I go back to the question, can I substitute in a 0 now for h? And the answer is absolutely. So if I make that substitution, I have 2a plus 0 minus 3, and my derivative would be 2a minus 3. Find rates of change or derivatives at given values using a limit definition. What we're going to do is we're going to use a limit definition to find the derivative of the function at x equals 3. So if we're at x equals 3, that means our value of a is 3. And we'll substitute in that value of a into our limit definition to find the slope of the curve of the function at 3. Now, what's our function going to look like? Well, our function is f of x equals x squared minus 2x plus 3. So let's go ahead and do this. I'm going to write down my derivative at 3 is equal to the limit as h goes to 0 of f of a plus h, and a is 3, f of 3 plus h, minus f of a, again a is 3, minus f of 3, over h. So I have the limit as h goes to 0, and in my function, I'll replace x with 3 plus h. So instead of x squared, well, I'll have 3 plus h squared minus 2, instead of x, 3 plus h, and then plus 3. And now I'm going to subtract, and I'll subtract f of 3. Well, my function is x squared minus 2x plus 3, or 3 squared minus 2 times 3 plus 3. And I'm going to divide by h. And what I'm going to notice is that I cannot substitute a 0 in for h. So I'm going to see if I can multiply through the terms in the numerator, get a bunch of cancellations so that I can eventually cancel the h. So this is where the algebra kicks in. I have the limit as h goes to 0. And if I allow my eye to look right here, I'm going to multiply out 3 plus h squared. Well, when I do, I get 3 squared, which is 9, plus 3h doubled, that's 6h, plus h squared. Then what am I going to do? Then I'm going to distribute the negative 2 to both terms, and I'll do that right here. So what that looks like is negative 2 times 3, which is negative 6, negative 2 times h, which is minus 2h, and then plus 3. Then minus, well, let's see, 3 squared is 9, minus 6 is 3, plus 3 is 6. And then I divide by h. And you may think I'm making things worse, but look what happens when I go to simplify. First of all, just look at the constants. 9 minus 6 is 3, plus 3 is 6, minus 6 is 0. These four numbers add up to 0. Also, just take a moment to check out the following. And check out that you can combine 6h minus 2h and get 4h. So what are we left with here? Well, we're left with h squared plus 4h in the numerator over h. Now, strangely enough, that's really what I was trying to get to, because I want to be able to factor an h out of the numerator to cancel with the h in the denominator. So I have the limit as h approaches 0. I will do just that. I'll factor an h out of the numerator. That leaves me with h plus 4 in parentheses over h. And then I can get that cancellation I was looking for. So now I can evaluate directly, right? Because I have the limit as h goes to 0 of h plus 4. And if I can evaluate directly, all I'm saying is that in place of h, I'm going to substitute in the 0. And it looks like my derivative at 3 is equal to 0 plus 4, which is 4. And what does that mean, ladies and gentlemen? If I graph the function and just check out for a moment, x equals 3, and I draw a tangent line, the slope of that tangent line is 4. Thank you. From the graph of the function shown, we want to estimate each of the following: f of 0, f of 2, the derivative of f at 0, and the derivative of f at 2. Now, what's the difference between the two notations? F of a, this refers to the y-coordinate at x equals a. So all you'll do is look at the point, wherever that may be located, and simply read off the y-coordinate. So f of 0, I see a point right here. The coordinates of that point, 0, 1. So f of 0 is the y-coordinate at x equals 0. That's 1. For f of 2, I see a point right here. Coordinates at that point, 2, 1. So f of 2 is the y-coordinate at x equals 2. That's 1. Now the derivative at a, this refers to the slope of the tangent line at x equals a. So that means I'm going to have to draw the tangent line at x equals 0 and at x equals 2. So if I'm looking for the derivative at 0, I go to x equals 0 and I draw a line that's tangent to the curve there. And I try to read off the slope of that line. Slope of that line, well, that looks like that slope is 0 because the line is horizontal. When I take a look at the derivative at 2, again, I'm going to draw a tangent line to the curve at x equals 2. And when I do that, I try to estimate its slope. Well, let me see if I can grab 2 points on this line, and it looks like I'm going right 1 unit, and it looks like I'm going up 4 units. So my slope would be rise over run, which is 4. So I'll estimate the derivative at 2 to be that slope, which is 4. Solve applications involving average rates of change. When you have applications involving average rates of change, there are many ways average rates of change could be looked at. First of all, if I go ahead and take a look at a curve like we have here, and I want to look at the average rate of change between x equals a and x equals b, I think about that old change of output per change of input. When I take a look at the change of f, that's the change that I'm marking right here. It's f of b minus f of a. So when I take a look at my average rate of change, what I'm actually seeing is a change of f over change of x, which is f of b minus f of a over b minus a. And you're probably thinking, gosh, that looks a whole lot like what? It looks a whole lot like a slope formula for the line segment connecting from x equals a to x equals b on the curve. And that's what you're seeing. It's the slope of the line through the points P and Q. Now, we can also call this average rate of change a difference quotient on an interval a to b. But it's still the quotient of differences between f of b minus a and b minus a. So my difference quotient, I can write as f of b minus a minus f of a all over b minus a. That's the same formula we had a moment ago. And again, if I go ahead and just draw a secant line from point P to Q, here this difference quotient represents the slope of that secant line. So again, to make sure that I'm communicating with you, I want to emphasize that you are looking at units for the change of f, and that's the units in the numerator, over the units for the change of x, and that's units in the denominator. So our units are going to be units of f of x per units of x. So if we're looking at a specific application for average rate of change, or a way to view the difference quotient, which is the same thing here, imagine the price of gasoline varying over a 2-year period. So f of x is the price in dollars, and x is the number of months since January 1st, 2017. Now, how do I use average rates of change to interpret the following? That the price of gasoline was increasing by an average of $1 per gallon per month from x equals 4 to x equals 12. Well, if this function here, which is y equals f of x, represents, again, price per month, then I'm going to go ahead and just take a look at the points at x equals 4 and x equals 12. And if I connect them with a secant line, the slope of that secant line is my average rate of change. And that's going to be $1 per gallon per month. So you can actually see that what actually happened was that if you're starting at, and grab yellow here, 4 months, well, the price dropped and then it went up. But the average over that 8-month period was an increase in $1 per gallon per month. Now, the very last way I want to look at average rate of change is by really formulating a way of allowing the 2 points to be designated by a and a plus h. You say, well, that's a little weird. My response is not really. If I start at x equals a on the curve, and if I pick the second point h units away, then I can go ahead and talk about the average rate of change between the 2 points by, again, looking at the slope of the secant line connecting them. And you're still looking at a change of output per change of input. You're looking at f of a plus h minus f of a. And then when I go ahead and take a look at the change of inputs, I have a plus h minus a. And notice those a's cancel. And my average rate of change formula, or my difference quotient, has a different form, but it still represents the slope between the 2 points, which I'm just representing a little differently as a and a plus h. Thank you. Solve applications involving rates of change or derivatives. If I want to look at applications in physics, imagine a function s of t that measures position versus time. So the derivative would measure the displacement versus time, and that's the velocity of an object. And so we would write the velocity of an object as the first derivative of s of t. And so the velocity at a would be the derivative of s at a. For a business application, imagine c of x is the cost to produce x items. So the derivative, which is called the marginal cost, the derivative of the cost function, is basically your change of cost for the next item produced. So the marginal cost of 100 items, the derivative of the cost function at 100 items, is the predicted cost to produce the next item, which is the 101st item. And you can have the same type of derivative thought process for revenue and profit, where marginal revenue and marginal profit are the derivatives of revenue and profit, respectively. So our question is, we know the revenue taken in by selling x number of fire extinguishers is given by r of x is equal to 2x squared plus 5x. Find and interpret the derivative, which is the marginal revenue, at x equals 10. So we know how to take the derivative. We've done this before. My derivative at 10 is the limit as h approaches 0 of f of a plus h. Here a is 10, f of 10 plus h. And it's actually not f, is it? It's the function r. So let me make that correction. r of a 10 plus h minus r of 10 over h. Now I'm just going to go ahead and substitute in 10 plus h everywhere I see an x in my function. So I have the limit as h approaches 0 of 2 times 10 plus h squared plus 5 times 10 plus h. And to make sure you and I are having the exact same conversation, ladies and gentlemen, what we just did was we looked at evaluating r at 10 plus h. So now we're going to subtract So when I subtract, that'll be this subtraction symbol here. And what I'm going to subtract is what? I'm going to subtract r of 10. And so I'll subtract 2 times 10 squared plus 5 times 10. And I'll divide by h. And I'll look to see if I can evaluate, and I can't. I cannot substitute in a 0 for h. It makes my denominator equal to 0. So I'm going to have to multiply through and see if I can get a bunch of cancellations so that eventually I can factor out an h from the numerator and cancel it with the h in the denominator. So I have the 2. 10 plus h times 10 plus h is 10 squared, or 100, plus double 10h, that's 20h, plus h squared. And then I'm going to distribute the 5, so that's plus 50 plus 5h, minus, now twice 10 squared is 200, plus 50 is 250, over h. Still not done dealing with the numerator. I'm going to multiply through by 2. So this gives me 200 plus 40h plus 2h squared. And then I have, again, plus 50 plus 5h minus 250 all over h. And you may be thinking I'm making things worse, but I promise I'm not. Do you see cancellations in front of you? 200 plus 50 is 250, minus 250 is 0. And I'm also going to go ahead and take a moment to say, gosh, I can take 40h and 5h and combine terms. So now I have the limit as h approaches 0 of 2h squared plus 40h plus 5h, that's plus 45h, over h. That's what I was trying to get to, ladies and gentlemen, because now I'm going to factor out an h from the numerator. So I have the limit as h approaches 0, and if I factor out an h from the numerator, I have 2h plus 45 times h over h, and the h's cancel. So when I look at the limit as h approaches 0 of 2h plus 45, I've gotten down to where I needed to get down to. Because what will I do? I'll replace h with 0. And it looks like I end up with what? I end up with 45. 45 is my marginal revenue at 10 units. Now I have to interpret. What's the interpretation? Well, I found the marginal revenue at 10. Now, revenue is how much I take in sales. So when I sell that's right, 11th fire extinguisher, I'll take in $45 in sales. Thank you. A car leaves an intersection. The distance it travels in miles is given by the function f of t, where t represents hours. Explain the following notations. The function evaluated at 0 is 0. The derivative evaluated at 1 is 60. The function evaluated at 1 is 70. And the function evaluated at 2.5 is 150. Well, let's first start by looking at the notation. The ordered pair t f of t refers to the time traveled in hours as the input, and the output is the distance driven in miles. As far as the derivative is concerned, t followed by the derivative at t represents the time traveled in hours as the input, and the output is the velocity. And the velocity is the change of output per change of input, so this velocity is measured in miles per hour. So when the function is evaluated at 0, the output is 0. This means at 0 hours, the car has traveled 0 miles. When the derivative is evaluated at 1, the output is 60. So this means when the car has traveled 1 hour, the car is traveling with a velocity of 60 miles per hour. When the function is evaluated at 1, the output is 70. So when the car has traveled 1 hour, the car has traveled 70 miles. So I suppose at some point that car must have been going faster than 60 miles an hour. And when the function is evaluated at 2.5, the output is 150. So when the car has traveled for 2 hours and 30 minutes, the car traveled 150 miles.